Good morning and welcome to this next rendition of Nano Explorations. My pleasure today is to welcome Junyi Zhu from Stephanie Mueller's group. His talk on integrating object form and electronic function in rapid prototyping and personal fabrication will start in just a moment. I just want to make sure I remind you that if you have any questions, please hold them to the end of the talk. At that point, you can either raise your hand and I'll call upon you, or you can send your message in chat and I'll make sure I relate it to Junyi. That being said, I noticed all of you already have turned off your videos and muted yourselves. That's the way it should be. And Junyi, please take over.
Okay. Thank you for the introduction. Hi, everyone. Welcome to my talk. My name is Junyi Zhu. I'm currently a third-year PhD student at MIT CSEL, HCIE group, working with Professor Stephanie Mueller. Today, I would like to share some of the recent research works on integrating object form and electronic function in rapid prototyping and personal fabrication. Rapid prototyping is a key technique that enables users to quickly realize their digital designs, therefore being widely used in early stage prototyping and small-scale customized fabrication. It mainly consists of the additive manufacturing, like the 3D printer, and subtractive manufacturing, like laser cutter and CNC milling machines. The first years, they are all big machines, like the early stage computers, very expensive, so are used mainly in industrial. Then about a decade ago, desktop level machines start to kick in and make the personal fabrication techniques more affordable and accessible more than ever before. Now that normal users are able to design and prototype like professionals. And this is also one a lot of HCI researchers starts in this field. So far in HCI, rapid prototyping has mainly focused on fabricating passive objects for which the form of an object can be freely designed. A lot of works on techniques for ultra-fast form design iteration, where you can make the trade-off between the object fidelity and fabrication time. And some are exploring on new materials like 3D printing fabrics. I would like to expand the spectrum to not only the object form, but also digital specifications and fabrications of object functions for interactive design. My vision is creative interactive object for which all functions are directly integrated with the form and fabricated in one go. Let me tell you a little bit more about this. So this offers the promise that eventually in rapid function prototyping, the interactive object form and function will be under the same design consideration. Therefore, the object form can follow its designated function and function adapt upon its physical form. I further identify some of the challenges towards this vision, the puzzles that's been missing. But first, there will be a 3D design environment for digitally design and the object and electronic function together. As the same importance goes to needs the physical prototyping platform for electronic and circuit design in the context of object form. Last but not the least, we will need a rapid fabrication technique for fast design iteration and high degree of freedom that produce both object form design and function design so that you can have accurate interactive feedback in a very short time. Here are my proposed solutions: Morph Sensor, curve boards, and lay sensor. For today, I will be mainly talk about Morph Sensor and curve boards that are published just this year in the top tier HCI conferences, ACM, CHI, and WIST. Let me start with the 3D design environment for digitally designed object and electronic function together. Morph Sensor, a 3D electron design tool for reforming sensor modules. Morph Sensor contains two parts: a 3D electron design tool for design electronic function in the context of physical prototype, as well as a fabrication pipeline to rapidly fabricate the resulting morphed sensor. Let me take you through the system walkthrough. Look at the 3D editor first. User was starting by importing the sensor modules from the Morph Sensor database. In this case, an air quality sensor. The system will then extract the sensor information from the board and schematic files, then subsequently create a board and individual electronic components as a set of 3D models. A bit background here, when you look closely at the sensor module, not all components contributes to the actual sensing. That's why the system provides the functionality of identifying active sensing components for you. The active components, sensing components, are generally more placement sensitive because that's where the sensing happening. And the components are not highlighted. The passive components, like the resistors and capacitors, can be more flexible in terms of the placement. And they typically can go to the space where the space is available. Users can snap and arrange individual electronic components on the 3D models using common 3D editing tools. Morph Sensor also offers the auto placement functions to use as a design starting point. During the entire editing process, Morph Sensor maintains logic connectivity by tracking the logically connected pin locations and display a 3D air wire between the pins, along with the prototype geometry in real time. The logic connection information was extracted from the schematic file of the sensor. After positioning the electronic components, user will connect the physical wires based on the logic air wire. Once the user connects the drawn wire to the pin, it completes the connection, and this is indicated by rendering a newly drawn wire in silver, and the corresponding air wire disappeared. User can go ahead and finish the wiring. User can still freely change the component location and the rotation at any time during the editing process. Moreover, user can expand the design anytime by importing additional sensors and components, in this case, a microcontroller and an LED displaying LED. Similar as before, users snap newly added components on the board and connect them to the remaining circuit. When the wire crosses, Morph Sensor automatically adds a wire jumper, allowing both wires to be spaced out sufficiently. When satisfied with the design, you can now export design for fabrication. You do that by using a lasso tool for marking up the area on the prototype the design would like to fabricate. The system converts the 3D circuits into a 2D projection through surface unrolling. Morph Sensor displays the 2D projection next to the 3D model and export it as an SVG file. Now that you have the digital designed sensor ready, let me show you how to fabricate them. Well, to obtain a high fidelity prototype, designers have the option to convert the SVG file into Gerber files, where the unrolled surface outline is the board new shape, and then send them to professional PCB manufacturers as a single layer flexible PCB design. However, the typical turnaround time for this process is around 2 to 4 weeks. And if you are one of the unlucky folks who happens to living through a pandemic, good luck on that. So while this might be good for the final designs, they're certainly not ideal for prototype design iterations. Therefore, we offer this fabrication technique that can produce relatively low fidelity prototype using prefabricated PCB footprints, which are essentially slightly bigger SMD footprints for better connection, and the silver inkjet printing, which can be made immediately on export. Let me go through this in more detail. Well, first, by inkjet printing an exported circuit. This is a normal office inkjet printer. All you have to do is empty the ink cartridge and fill with silver nanoparticle ink. Then you can print out the circuit traces instantly. You should put on some double-sided tape for later object attachment. Take out the big foot, soldering the corresponding components onto the big foot, and then apply the EECS tape onto the back of the big foot. This is the Z-axis tape that only conductive to the Z direction. And then attach the components to the circuit, and then you have it, the fabricated morph sensor. Next, you will go ahead and cut out the sensors and attach it to the object. That's the whole fabrication pipeline. If you don't even have an inkjet printer, no worries. You can use the export SVG file and make a circuit stencil. And directly using a conductive ink pen to draw on the object. This is a nice, even lower fidelity alternative method for fabrication. Similar to before, you will attach the components with Bigfoot onto the drawn circuit, and then have a working morph sensor. We used morph sensor to prototype a range of interactive devices, highlighting different levels of complexity. Let me show you some of them. This is a glass design that detects excessive blue light exposure and alarms the user. It is achieved through the blue light sensor and plus the microcontroller and the display LED, so that your eyes are always protected. Also have the soldering iron that will detect the level of the smoke in the air. And this is done through the air quality sensor. When the red LED blinks, it will warn the user of bad air quality. That's the time you should take a break from the soldering. We also implemented an N95 mask that can detect if the substrate is overused and needs to be replaced. Again, this was done through the humidity sensor directly integrated with the facial mask. Also have this AirPod design that can non-intrusively measure user behaviors, daytime and nighttime. Because they're such widely used object, and I have definitely seen people just wearing them even without playing music. And this was achieved by integrating an accelerometer directly onto the AirPod. Well, that is the morph sensor 3D design environment for object form and electronic functions. However, this will be perfect for when you kind of knowing what functions you are prototyping. But what if one are not even deciding on the functions? That will lead to a prototyping platform. And this, for me, leads to the curve boards. Let's look at the prototyping platform. Before we jump into the curve board concept, let's first take a look at how people do early stage circuit prototyping and interaction design nowadays. Not surprisingly, breadboards. Breadboards are great. You can easily plug and unplug electronics and repositioning the components, which leads to high function flexibility. You can also switch them between projects, which results in high reusability. However, while testing a function on a physical prototype, they don't usually integrate well with the physical prototype form. One alternative is to use protoboard and or customized PCB board. They fit to the physical object better. However, once fabricated, it is impossible to move, almost impossible to move components around. Each design iteration requires soldering and desoldering, which is time consuming and leads to low function flexibility. This holds true even for the morph sensor that I just presented. It may be saved the soldering and desoldering time, but still it's quite time consuming. Question remains, is it possible to keep the function flexibility of breadboards while also integrating well with the form of the prototype? Well, my solution is curve boards, integrating breadboards into physical objects to prototype function in the context of form. Let me start by demonstrating some use cases that can be most benefit from curve boards. During the design of an interactive headphones, curve boards help narrow down component locations like buttons and knobs for most suitable control layout. Curve board also helps ensuring the components fit onto the prototype. During the design process of heart rate monitoring Trinity bracelet, curve board helps iterate through different functions and components, especially interactive components like OLED displays, and make sure they all fit onto the final prototype nicely. Curve board also preserves look and feel of the prototype. Curve boards allow user to prototype function directly on a small and dedicated object like ring, which is very hard to achieve on the normal breadboards. Fourth is preserving object intended function. As you can see, with all the electronics components on top of it, the frisbee still functions and functions as normal frisbee as it throws and spins. Curve board also help with identifying component needs for the prototype. With curve boards, the direct hands-on interactions, users are able to design an interactive teapot with temperature and T-shape monitoring, so that you will know exactly when the tea is ready. Cheers. Let me walk the curve board system with you. Again, curve board contains mainly two parts, one interactive 3D editor for designing the curve boards and a fabrication method that's associated with it. Let's look at the 3D editor first. User will start by load the 3D model into the system and convert it into a set of pinholes. Notice that each of the gray dots on the object is a potential pinhole position for users to select. Next, we'll create the board layout by adding the VCC, ground, and terminal channels directly on the object. Once satisfied with the design, we'll export file for fabrication. Notice that all the pinhole layouts are as indicated by users. And the inside, all the channels are interconnected as designed. Curve boards also provide automatic channel layouts to use as a starting point. Then you can add and delete channels on top of that. As shown here are 3 different object prototype designs that's being generated through automatic layout. We envision this to be like the auto wire function in common EDA designs, that you use it as a reference and keep on editing on top of it. Let's move on to how we actually fabricate the curve board design. Well, the most ideal fabrication method is to completely 3D print it with the conductive and non-conductive dual material 3D printing. So I went ahead and tried a bunch of different printers, companies. The most close one that we could find at this point is this company called ACEO. They are able to print the general purpose silicon and the conductive silicon in one run. However, even with them, the technology is still under development and currently limited by its printing volume, and the printing out conductive silicon has relatively low conductivity, which can only light up LEDs, but not other more complicated communication protocols. As a result, we have to figure out something else for most of the cardboard design fabrication. This is the alternative technique that we do with the 3D printing plus the conductive silicon. We will start by 3D print the cardboard housing exported from the cardboard system. Then prepare the conductive silicon for injecting into the housing. By that, we mix the carbon fiber into the silicon part A first, stirring for 5 minutes, adding the silicon part B, and stirring for another 5 minutes. Then transfer the made conductive silicon into a syringe. Then we fill the conductive silicon into the cardboard housing. Although this fabrication method works nicely, in the future, we still envision that the cardboard will be mainly produced by the 3D printers and prints everything in one round. Although with current limitations, the technology is right at the doorstep. After the fabrication of the cardboards, we will apply the surface coloring to visualize the channel layout. For most of the cardboards we built, we used hand-drawn markers to directly mark on the cardboards for the saving of time. For more advanced users, you can also use the 4-color 3D printing technique, like for the printer like the Da Vinci 3D printers, to print out the design with the color on it. Well, that is the cardboards, the physical prototyping platform for circuit design in the context of the object form. Next, I would like to introduce more about the laser sensors for the fabrication technique for fast design iteration. But unfortunately, I haven't finished building it, so I only show a drop of the early results. As mentioned before, some of the fabrication techniques, like from the Morph Sensor, it works pretty nicely. However, there are still some limitations, like, for example, the prefabricated footprint, although quite small already, but compared to the bare SMD components, could still interfere with the object shape. Moreover, the circuit we're producing are more like the 2.5D circuits, which limits the function design complexity and lower the integration levels between object form and the potential functions. So I'm looking at how to build the actual 3D sensors. Some of the early results showed on the left, basically I mixed this type of silver iron solutions, and it can react under certain wavelengths of the laser beams, which make extraction of the silver particles in the solution. And I take the inspiration from the lithography or bubblegram and the laser engravers to see if we can mix them together into a 3D block and directly etching circuits inside the 3D objects, so that we can have a truly integrated design with the sensing and traces inside of the object. All of those are cool. Hopefully, I convince you that by now. So what? What are these techniques going to be used for? What are the bigger pictures and real world impact? How can creating highly customizable interactive object that functions are directly integrated with the form and fabricating in one round be beneficial? Well, let me zoom out a little bit. Prior to MIT, during my undergrads in University of Washington, I worked on some of the health sensing and monitoring projects. For example, this TMAP on the left, measuring hemoglobin levels and screens for anemia non-invasively through the camera and the LED lights on the phone. On the right, the Sesamon measures blood pressure through camera and the microphone. And one thing that I learned from all those projects from the health sensing is We as human beings, we're all unique as we are all highly customized. So that's why I'm thinking this is the perfect place where our technique can shine. The highly customized health sensing system for every individual's unique individuals. Some of the ongoing project, this was a EIT system built for measuring the muscle strain levels. It will be measuring mainly used for recurring monitoring and potentially prevent the injury. This is in collaboration with the Harvard MGH team. It's because everyone have a very different settings, I guess, on your arms and legs, and the place you're measuring have a very specific muscle layout. So a highly customized devices with fast design iterations can certainly help. We're also trying to establishing other collaborations across MIT campus for some potential opportunities. So now that I show you the 3D design environment for digitally designed object and electronic function together, namely the curve board, I also showed you the physically prototype platform for electronic and component circuit design in the context of object form, in which case is the curve board. I show a drop of the rapid function techniques for fast design iteration, which hopefully I'll get the chance to show in the future. And all of those efforts contributes to my bigger vision, which is create interactive objects for which all functions are directly integrated with the form and fabricated, can be fabricated in one go. Well, with that all being said, I would like to thank my advisor, Professor Stephanie Mueller from HTIE Group. I would like to thank some of my previous mentors, Professor Shriley Patel from UW, Dr. Edward J. Wang from UW, and currently a faculty member at UCSD, and my mentees, American students and Europe students. I would also like to thank MIT.nano and NSF for providing some fundings of my project. Thank you. I'm ready for the questions.
Junyi, thank you so much. That was a very interesting talk. You're looking at the very applied ways of using your technology, ways that would indeed potentially be transformative for our everyday experience. And that itself is a very important thing to pursue. Many of your technologies elegantly use today's existing electronics and then provide a clever underpinning that connects that electronics in a way that was not done before, or at least in a very conformable way. You mentioned some examples. Are there first opportunities beyond medical sensing that you're observing now? Are people saying that this should be a common function in everyday devices like phones or iPods that you mentioned? For example, your accelerometer, is that something that simply Apple should start introducing in their iPods?
Yes, I think that definitely helps. I think for me, the techniques we produce is, I certainly hope that some of our project can inspire some of the industrial companies to, shifting towards that position. For me, the fabrication techniques and design systems are mainly for the early stage prototyping designs. And those things can be beneficial for mostly the individual persons that have relatively lower expertise in the technical. For example, if you are well familiar with the Altium Designer or Eagles, you might as well design a flexible PCB on your own for each of your project, although they still take a long time. But I think the technique can also be used for as you said, like for the bigger level. So imagine, I think we have a survey basically to see how Kickstarters, the companies, the startups, how they functions through a bunch of through the time. And the thing that we noticed that the time is money, and a lot of those small scale companies does not survive through the first few years. And imagine using this kind of technologies to speed up their early prototyping rapidly. That might save, hopefully save some of the companies from went bankrupt. So mainly it's for the individual users, but I see the potential of applying that to other fields, even in the industrial fields.
And you see that the needed platform is the digital design that you provide, and the 3D printing could be outsourced. Hence, others do not have to actually own the physical infrastructure. They could just start with the digital infrastructure to design and then obtain a physical infrastructure.
Yes, exactly. And if you think about it, you will still, once you design something, you always have to order something like the sensor modules or components. I envision that in the future, all of those can be integrated together. And once you place the order, you're essentially ordering not only the sensing, you're also ordering the form with it. So,
Excellent. This is everything you described here is for humans, individuals, carrying this sensing technology or design technology. Do you see it being exploited or utilized beyond the humans, the built environments, sensing of the agricultural performance and such? Would there be a benefit there? Again, you say, it's good to be able to do rapid prototyping of these ideas. I would imagine, especially in opportunities like that, the aesthetic design might not be quite as important, and consequently, even some of the very rapid prototypes might be all that's needed.
Yes. Yeah, I think that's a very interesting aspect. And I think especially for the agriculture, because when you think about it, United States and most of the developing countries have very sophisticated monitoring fields and the environment. But for across the world, there are so many different environments with different degrees of complexity. And I'm sure some of the, so in a way, they're all highly customizable. So I think with that, this technology can certainly be beneficial in that field. I would love to explore some of that in the future.
Well, thank you very much for showing us this today. Indeed, the immersion lab of MIT.nano might find benefits in being able to compare some of the present sensing technologies in the immersion lab with your sensing technology, and hence be able to get better correlation between what we truly experience and what the world perceives we experience. Junyi, it's been a pleasure to have you. I very much hope next couple of years of finalizing your PhD degree go extremely well, and hope that we can have you back at some later time when the next stage of your technology gets developed.
Thank you so much for having me. I would love to come back in the future.
Thank you. Well, at this point, I will conclude the present Nano Explorations. I will also remind you that we will, at this moment, with this seminar, we will indeed take a pause in the Nano Explorations for the month of August. Let everyone enjoy the summer last month before indeed the school starts. And we will return in the fall with the next set of Nano Exploration talks. With that, thank you all for attending today. Take care.
Thank you.